Cool. Good evening, everyone. Thank you for joining this online webinar. I weekend, so and also I taught a 3-hour lecture this morning in the boot camp, so my voice might sound a little broken. Apologize for that. And also, if you hear like kids crying, I just my 4 months old son, so and that's kind of out of my control. So my name is Zeyu. I manage the product and also engineering team at the NYC Data Science Academy. I'm also a data science instructor in the bootcamp. So today we'll go through the Kaggle workflow. So if you sign up for this webinar, I assume you already have maybe attend one Kaggle competition or looking forward to get a better ranking on Kaggle. So I used to be a very active Kaggler, but now I pick up more responsibility in the company, and also my son was born, so I don't really have time for that. But maybe later on I can join more competitions because there are more like deep learning competitions on Kaggle now. So it's very fascinating. All right, so the agenda of today's webinar, we have 4 parts. So I've basically explained like how Kaggle competition works, and also the 3 major parts of perform better in Kaggle competitions, how to do feature engineering, how to do parameter training, and also eventually once you have more models, you probably want to ensemble and also stack your model. So for the instruction part, we do have a section here in Adobe Connect. Oh, I need to zoom in. Okay. So,
yeah.
Okay, is it better?
Yes, perfect.
Okay.
Yep.
So there's a instruction in Adobe Connect, and also I posted an announcement on Meetup. So you can just follow instruction here. You have a Gmail account, have a Kaggle account, and then I share the notebook. It's on Google Drive, and you can use the Google Colab. That's the main topic of today: how to use Google Colab to hack a Kaggle competition. Because Google Colab is pretty new. Google released it like last year, and it gives you free access, immediate access to a so-called Docker container. Have most of the popular machine learning packages ready. You can just start hacking the competition right away. So that's actually perfect for this kind of online session. So we don't need to talk about how to install packages on a machine or handle all the technical issues. So again, this one I think this webinar only have like 40 to 45 minutes. So I will now talk about what is multiple linear regression or what is a random forest. So I will just go through this notebook high level, and so hopefully you can learn something from this webinar, and also again maybe do a better job in the next Kaggle competition. So if you click this link in the instruction box as well, you can open this notebook with Google Colab, and the default mode is just like everyone with the link can view it. But if you want to take notes or make changes, you just need to make a copy on your own Google Drive. So the first part, how does it work? How does Kaggle decide who is the top winner of the competition? Well, usually most of the competitions, they have 2 leaderboards, one called private leaderboard and the other one called public leaderboard. So most of the competitions, they have a training.csv file and also a test CSV file. So yeah, they do offer free GPUs. Yeah, so they have a so-called public leaderboard and also private leaderboard. So for the competition that we're going to use today is a housing price prediction competition. Actually, it's just like the machine learning project of the bootcamp students. So if you look at the leaderboard part of this competition, you'll see a private leaderboard and also a public leaderboard and also private leaderboard. So, but the competition is still like ongoing. So that's why the private leaderboard will be decided after the competition ends. So for the public leaderboard, you can see here, the leaderboard is calculated, approximately 50% of the test data. So 50% of the test.csv file that you don't know what the target variable is. And the final result will be based on the other 50% of the test CSV file. So that means, even if you got top 1 on the public leaderboard, it doesn't guarantee that, you got the same ranking on the private leaderboard, because you don't know which 50% they're using for the public leaderboard. And you can only submit at most 5 times per day to the Kaggle leaderboard. So you can only test, a limited number of times. But this is not always the case. So here I have a breakdown of the different structure of the Kaggle competition. So here we have the x-axis as a time series. So the most common layout are like the two on the left-hand side. So you have most of the data, all the data they were sampled or collected on the same time frame. So, but sometimes if you have a much larger training data set and a relatively small public test set, so in this case, you probably should not trust the public leaderboard, because you might be overfitting this public leaderboard. Okay, so training set is much bigger. Well, in some cases, the size of the public leaderboard and also the the training set and also the public leaderboard, they're almost the same. So in this case, well, you can use, actually most calculators use the public leaderboard as a so-called K+1 fold of your cross validation. And okay, so in some of the competitions, actually the data was collected in a different time frame. So I remember there was a Zeyu competition. It was like, I think the end of 2017. So I ended with like 200-ish. They only picked the first 100 for the final round. So I was a bit unfortunate, because I was also helping bootcamp students with their capstone projects. So I didn't really have time to tweak my model. But anyway, so for the Zeyu competition, it was the reason why I mentioned that it's a $1 million competition. So it was kind of like a little bit misfortune. Anyway, so for the time series graph, so for the Zeyu competition, the training set was using the first 6 months of 2017 data. So they want to predict the so-called Z estimate. And the training set was using the first 6 months of 2017. And for the public leaderboard, they were using the second half of 2017 data as a public leaderboard. So you don't know the results until the beginning of 2018. So then they decide, okay, so the top 100 Kagglers get to the so-called final round of the competition, and then the data was going to be using the first 6 months of 2018 data as the final round of the competition. So in that case, you have to trust the public leaderboard, because the data set was collected at a different time frame, and that's the only reference you have. All right, the previous graph might look a little bit confusing, because sometimes I can trust my leaderboard, sometimes I can't. So, and also then the question is, should I trust my cross-validation score or the public leaderboard score? So a typical question on a smaller data set, for example, the one we're using today, the housing price prediction computation, is a relatively small data set, but it has rich data, so rich features. So that means you can do a whole bunch of feature engineering on top of it. So a very typical question on a small data set is, I'm doing proper cross-validation locally, and I do see improvement on my local cross-validation score. However, the public leaderboard does not correlate at all. So this happens because when you run local cross-validation, when you do the k-fold, either 3-fold or 5-fold, and each fold is getting much smaller, because it's already a small data set. And if you divide into 5 folds, each fold is getting even smaller. So in that case, it's like sort of like random. So you can get a much better cross-validation score just because you use a better random seed. So and in that case, you should only trust the cross-validation score. So eventually, most top Kagglers pick is find the solution, the submission that has the best. So it's actually it's a formula. So you have the local cross-validation score, and also you have the public leaderboard score. So you just pick the final prediction, final submission is based on this sort of like formula. So you put a different weight on your local cross-validation score and also the public leaderboard score. So usually 50-50 is enough. So because eventually you might have multiple submissions and it give you like different public leaderboard score. However, it also gives you different local cross-validation score. So most of the time, people just taking the average, see which one has the best performance on both the local cross-validation and also the public leaderboard. And trusting C cross-validation is the hardest thing to do. Trust me, I have been there because those CFC submissions, they get a much better public leaderboard score. However, you cannot trust it because for example, in this case, you're definitely overfitting the public leaderboard. So so you just need to make sure using this kind of like, it's not a magic formula, it's just like take both the public leaderboard and also cross-validation score into consideration. All right, so that's how it works. So any questions so far? Oh, you're handling the track? Okay, cool. So yeah, because I don't really have time to go through like what is cross-validation, like what is flow. So hopefully you already have some like background, so we can make this we can go through more advanced topics of this this webinar. All right, so talk about pre-process. Let me try to hide this my credentials a little bit. So because this is a copy of the notebook that I shared with you. So I don't I just mark them as X. But if you want to use Google Colab to hack, no, they're not public. I make a copy, so make a copy. So the one I share with you guys don't have their credentials. So if you want to use Google Colab to work on the Kaggle computation, you need to create a so-called API token. It's pretty straightforward. You go to the Kaggle website, click your avatar on top right, and then go to My Account. And here you have the two buttons. One's called Create New API Token, and can expire existing API tokens. So and then we'll download a so-called Kaggle.json file. In that file, you can find the username and also the so-called the key, the API key. Then you just copy paste from the JSON file to this code chunk, just replace them. So I just hide it. All right. So once you run this part, so you'll see on the top right here, it says connecting, initializing. It will initialize a Docker container behind the scene, and it has most of the packages you need to use for Kaggle computation. However, since it's free, it also has limitation there. For example, you only have 12 gigabytes of computer RAM, and also like 25 gigabytes hard drive available there. And if you open the left-hand side, you can see the this is like the table of content of this notebook. So it's decided by those markdown code chunks. So those are just the headers of the notebook. So code snippets and files. So you probably don't see this, but we'll get there. So if you run this part, it will try to download. Oh, not authorized. Let me try again. Oh, okay. I think I probably messed up, so I need to replace my key again in case it only has one key available there, I believe. Okay, works. So here you have download those sample submission CSV test training and also data description. So if you don't see it on the left hand side, you just click refresh. Sometimes it'll take a while to show up, and you'll be able to see the files, you just download it. And then this is a notebook as well, so you can run Linux command in this notebook. So you just need to put the exclamation mark before the next command, so then notebook will know this is a Linux command rather than a Python command or a Markdown code chunk. So then you can see here, this is the drive within the so-called Docker container. And then you can use ls. If you're familiar with Linux, you know what I'm talking about. It's just running those Linux commands within the Jupyter notebook. So a very cool feature of Google Colab is you can actually mount a Google Drive to the session. So because the thing is, like, sometimes the data might be huge, the computation data might be huge, so you don't really want to always download data from scratch. That might take like 1 hour to do. So you can preload, you can upload the data to your own Google Drive, and so-called mount your own drive to this session. I'll comment it out, but you can also uncomment it. So it's just trying to mount your own drive, and then you can change the directory in this notebook session. So then it's called My Drive, and then you will be able to see everything on your own Google Drive on the left-hand side. All right, so I commented out because I don't really want to demo it during this session, but it's something you can do when you are working on own computation. And also, like, sometimes I know people like to save the pre-processed data, because pre-processing can also take a while. You want to handle those missing values, and also like do some feature engineering. So if that part is done, you just want to take care of the modeling part. So you can save the pre-processed data locally, and you upload to your own Google Drive, and then mount your drive to the session, so you have access to those saved files. All right, so for a quick demo here, oh, my Excel is running. Anyway, so I load the train CSV file, and just in case you haven't got a chance to take a look at the data set yet, you have the ID column, and this is like the column that we're gonna get rid of when we build the model, because it doesn't contribute to the modeling or to the prediction. Okay, it's just something like unique. And there are like 79 features. The reason why we picked this data set for doing the Kaggle machine learning project is because it has so many rich features, and it's a small data set. So even if you want to run some crazy stuff, like crazy stacking, crazy ensembling, great search cross-validation, it's fine because data set, but it has rich features. So that means the most important part of a Kaggle computation, which is feature engineering, is has unlimited options there. So the sale price is the target variable we're trying to predict. It's just the sale price of the house. So it has another 79 features we can use to predict the housing price. Some of them they're categorical feature, they're just strings, and some of them they're numbers. You also definitely have missing values there. They interpret as not a number in pandas data frame. So just remove the ID column, but before that we need to save it, because eventually we need to construct our summation CSV file. So we want to save the ID, but remove it from the data set. And then we have our X train, Y train, and X hat. We don't have the white hat because that's something we're trying to predict. Then after you save the X train, Y train, X hat, then you can feel safe to delete the original data frame, because again you only have a limited number of RAM and also hard drives. Sorry, just RAM, because when you read the CSV file, it will load the data sets to your computer RAM. So you want to delete those data frames, because the data you need, they're called X train, Y train, and also X test now. So you don't need these two data frames. And you can print out the size of X train and X test. So they're almost the same, and both of them have 79 features. All right, so before you run any feature engineering, keep in mind it's not always a good choice to combine the training and test. So here's the reason. For category features, this is fine because you want to avoid having new categories in your test set, which will cause dimension mismatch after you dumify the data set. So, so for example, if a category is only visible in the test set, then when you dumify the data set, dumify the test set, you will have one extra column there, and scikit-learn doesn't really want to take it because the training set and also the test set have different shape. All right. If you want to perform any transformation on numerical features like normalization or standardization, keep in mind you need to fit on the training set and also transform on the test set. So here's a link to I think Stack Exchange. So it explains why you should do that. And also, if you need more mathematical proof, you can go to the 7th chapter of ESLR to find the details. All right, so I'm going to. But for this demo purpose, I just concatenate our training and test. All right, step 2, feature engineering, which is the most creative part of data science. So let's start from Paragon feature because nearly always need some treatment, and also hard cardinality issue can create a very sparse data set. So hard cardinality means you have more than normal number of categories inside the column. So the basic approach might be one-hot encoding. So that just encode array of length k into a binary approach. So if you have k levels, so then you have, let's say, k minus 1 columns, and each column is just a binary number, 0 or 1. So 0 means that level is equal to true. Sorry, 1 means that level equal to true. So it's used with most linear algorithm, and I'll talk about why why it's good for linear algorithm next. So we also probably want to drop first column to avoid collinearity. For example, if you have a gender column that let's say is male or female, then those two features they're perfectly negatively correlated with each other. So in pandas you can either do that. And also, you can probably want to consider encode categories appear, let's say, only at least 3 times. So, because otherwise, it would be like, could be noises, could be typos. So, and you can reduce the feature, space with no loss of information there. So to quickly check the number of levels or categories in a column, we can iterate through all the columns in the data frame. We check if the type equal to object, because if it's not a numeric column, then it will show as an object in pandas data frame, and then we'll print out the number of levels. So one thing to know is that most of the part they have a reasonable number of categories. So however, for the neighborhood you have like 25. It doesn't make sense because the 25 different neighborhoods in Ames, Iowa. So, but the other columns it looks fine. Have like less than 10 categories. So to dumify, to use one-hot encoding in pandas, that's just pd.get dummies. And like we talked about, if you want to drop the first column, that's just trying to avoid collinearity. You can just say drop first equal to true. And also, if there's a missing value there, we will categorize a missing value or NA as another category. So dummy NA equal to true means you have an extra column for all the missing values. So then for most of columns here, let's say the I think in the neighborhood. Probably the zoning and also street. So the street is a categorical column. So you have street, it was pavement, or street NA. That means that column is a missing value. So it's all the binary representation. That means okay. So this observation, this row, the street equal to column, the value equal to pavement, and you can see the shape of this one hot data frame. So it used to be like 79 columns, but after one hot encoding, it becomes 288 columns. And even though it's still a Jupyter notebook, but it's in Google Colab, and it disabled some of the shortcuts in a Jupyter notebook. For example, you used to have like, if you move a cursor inside the function, you press Shift Tab, it will print out the quick documentation of the function. But inside a Google Colab, you just put 2 question marks in front of the function, so it will list the help function here. So now you can see here, dummy NA by default equal to false, and also drop first by default equal to false. All right. Next, label encoding. It's another way of dumbify categorical features. The advantage is it does not create dimensionality. The idea is very simple. You can you have, let's say, k levels, then you just assign a random number from 1 to k to each level. So it doesn't create any extra columns there. However, it's only useful for nonlinear tree-based models. Think about it. If you have, let's just try to run this one first, and we can use, I think we can use the neighborhood as example. So if you have neighborhood, like say we have 25 neighborhoods, remember? We encode them as 1 to I think 0 to 24. So if you use this number in a linear model, so that basically means okay, so neighborhood 5, neighborhood equal to 6. So that means 1 unit increase in the neighborhood will have times the beta coefficient for that neighborhood column will have the same effect on the housing price, which might or might not be true, because these numbers, they're randomly assigned to those categories, so you don't really know if it's true. Like neighborhood 6 is like just 1 unit higher, the house price is 1 unit higher than neighborhood 5. So if that's not the option, you probably don't want to use it. However, for the tree-based models, it always either through all the it makes more sense to for the tree-based model, it will either through all the possible values of the column to find the best split. So it doesn't really matter how you assign the number to each category. All right, so we also have ordinal features. So ordinal feature means there's some natural ordering in this column. So for some of the columns, we have the condition column. So usually we think about excellent is greater than good, better than average, better than fair, or poor. So we can construct a dictionary like this. So you have excellent as 5 is a Python dictionary, and then you can take all the ordinal features, ordinal columns from the data set, and then this is the dictionary we have. We want to assign each level a number. And then, so we have some kind of external quality, and where's my external quality column? Okay, so external quality column. So the first one is 4, the second one is 3. So that means the first one is good, the second one is I think fair or typical compared to the label encoding. the overall quality, the external quality used to be, for example, here 2 and 3. So here this external quality feature is an ordinal feature actually. So it makes more sense to give each category a number from 5 to 1. So for feature engineering, besides that, you can also create more interactions within the data frame. So what we can do is pick 2 columns, and you can start from what makes sense intuitively. Because the thing is, like, for example, if we can pick the garage condition and also the garage type, so these they're 2 separate columns. However, you can have a interaction between these 2 columns that becomes garage condition times garage type, and then the becomes another category, another column, and you have the for the number of category, that's just a multiplication of the number of categories of the condition column times the categories of the type column, and then we'll have the new column here. So winners usually find something that most people struggle to see in a data set, and trust me, not many people look at the data at all. So if you find some magic data column or magic pattern in the data set, then that's a key to winning a Kaggle computation. So the reason why this works is because think about in tree-based models. If you have let's say 2 layers. The first one, the first node, the node on the first layer, let's say it's based on the garage condition, and then the second layer is based on the, let's say, garage type. So you're actually just combining these 2 and tell the tree-based model, hey, think about these 2 instead. So sometimes it might save time, but depends on your computing power. You could try all the possible 2 interactions if you have enough computing power. But again, start from the interaction that makes sense intuitively. And this is especially useful when dealing with anonymous data set, which means the column name are unknown. So they're most of them, they're finance computations, so they don't really want to disclose the column names, so people can't find their what their business model is. So they just anonymize their column names, so they don't really know what the meanings of the columns, so you can only guess it. And in that case, trying this kind of interaction actually helps a lot. And depending on the situation, most of the time you can just treat NA missing values as a separate category. So I think we have maybe 5 more minutes left, and it's really
You got about
advanced webinar. So I'm probably gonna go through. So I think I should go through step 3, or I should stop here.
I think actually step 3 is probably a little bit better, and
Okay.
then we can. I mean, the rest is they could read on it anyway.
Okay, cool. All right, so after you've done the pre-processing, the feature engineering, then you're ready to build a model. So once you have a model, you probably want to find what are the best hyperparameters of your model. So what you learn from the college or from online free courses might be hey, you should run grid search cross-validation to decide the hyperparameter. Well, that is true. There's 0 effort or 0 supervision, but it also means enormous parameter space, and also at the same time it's very time consuming. So most of the Kagglers, they just pick one set of the parameters from Kaggle kernel that someone you publish the kernel or the notebook in the computation. So you can just borrow those hyperparameters, or you have a golden parameter used in previous computation. That's also a good starting point. And then you start with a parameter that does not affect others too much. For example, the learning rate in the boosting model doesn't really influence other parameter tuning from my experience. And also some of those hyperparameters, they're highly correlated with each other. So the maximum depth, minimum sample split, and also minimum sample sleeve in random forest model. Because think about it, if you have more depth, then definitely the samples you have in each node, or the minimum sample split will be definitely smaller. So these three, they're actually highly correlated. And also iteratively iterating the parameter, control overfitting or underfitting. If the parameter helps local cost validation score, try to tune as much as possible. Stop it if the cost validation score converges. For example, like you have maximum depth, so most of the time, if you have more depth, that means the model is getting more complicated. It tends to overfitting because the minimum samples each node is much smaller. So let's say at a certain point, even if you increment the maximum depth, it does not help your local cost validation score. So then you should probably stop training this maximum depth parameter. And also, you can also use the probability leaderboard as a k+1 fold to further prove it. There's a trade-off there. So we have a so-called trade-off between expert and also research cost validation. So it's called Bayes optimization. The idea is, so there's a link to the GitHub repository, and also you can see how you can use this Bayes optimization within sklearn. But the basic idea is, so for most of the machine learning problems, machine learning algorithms, you have a so-called cost function to minimize, or if it's a likelihood function, you probably want to maximize it. But either way, you either maximize it or minimize it. Then it will give you the best, let's say, the best beta coefficients of each feature. So the same thing here. So Bayes optimization is taking those hyperparameters as the features when you're training a machine learning model. However, this time, the cost function becomes the cost validation score. So think about, like, you keep changing the value of hyperparameters, you get a different local cost validation score, and your final goal is to find the best set of hyperparameters that gives you the highest local cost validation score. So that's something you can use for Kaggle competition. But again, even if you're using this Bayes optimization, still it's a little bit complicated, and still it takes time to run it, but it's definitely much more efficient than the research cost validation, which basically means you specify a range of or just a list of values for each hyperparameter, and go through it. Okay. So again, at the end of the day, the golden rule is finding the optimal configuration is not a good time investment. So that's just from my personal experience. So probably at almost to the end of the competition, you don't have any time to do, let's say, feature engineering. You only have a couple hours left. Then you might try, okay, what if I change the maximum depth hyperparameter and see how it helps? But usually it's not a good time investment. All right, so I think probably gonna end up here. We still have the last part, which is in some way stacking. These are like more advanced, topics. So if you don't really have experience with machine learning, you're probably a little bit lost at this moment. But signing up for the bootcamp is a good solution. The last one is my personal success formula. So 50% of time you will spend, most of the time do feature engineering, because this is like I said, is like the most creative part of data science. So 50% of time you'll be working on feature engineering, and 30% of the formula is depends on like the model diversity. So that's the stacking part, and also 10% luck. If you can find the pattern in the data set that someone don't really see it, because I also mentioned here, most people do not read the data. So not many people look at the data at all. So if you look at the data set, so actually one of the competitions, someone literally look at the data in Excel and find a data leakage there. So it's just something people a little bit reluctant to do it, because it takes time, and it's not always guaranteed you'll get the golden feature, but or the golden ticket. So 10% of kind of is luck, and also 10% of proper ensembling, which is the part I didn't really get a chance to cover.